This lecture will cover resolution artifacts. There are 4 resolution artifacts that you will need to know: axial, lateral, slice thickness, and speckle and noise artifact. You should be familiar with what axial resolution is. It's how well the machine can display objects that are in front of one another. So axial resolution artifact then is when the machine can't display those objects correctly. So it's created when a pulse intersects 2 close structures that are parallel to the beam or in front of one another and are displayed as one structure. This is going to happen because the 2 structures are less than half of the SPL, or the spatial pulse length, apart. So I know you've seen this diagram in previous lectures. So we have our individual reflectors going through the body here. We have 2 that are a little bit closer to each other down at the bottom here. As our sound intersects each of these reflectors, that sound is going to then bounce back and head back to the transducer. As long as those structures are more than half of that SPL apart, they are displayed as single structures, like they are in true anatomy. However, when we get 2 reflectors that are very close to one another, the machine can't tell them apart because they sit too close together and therefore displays those 2 structures as one. This is artifact because it's not displaying true anatomy. To correct it then, we just want to make sure that we're choosing the highest frequency possible for the penetration that we need into the body. Higher frequency transducers have shorter spatial pulse lengths, therefore they have better axial resolution. Lateral resolution then is kind of works in the same way. We know that lateral resolution is how well the machine can display things that are side by side. Artifact comes in then when the machine is unable to display things correctly. So lateral resolution artifact is created when a pulse intersects 2 close structures that are perpendicular to the beam or side by side and then are displayed again as one structure. This is also the reason that sometimes we see pinpoint reflectors are displaced as a horizontal line. True anatomy, it might look like this, but on the ultrasound, it would look a little bit more like a horizontal line. It's just part of the lateral resolution artifact. The whole reason this occurs is because the beam is wider than the distance between the structures. So again, we've seen this before. We have our reflectors. And as long as reflectors do not both sit within the beam width, then they are displayed as true reflectors. So here we have this reflector and a little bit of this reflector coming into our beam width. Because of that, the machine can't tell that they are separate structures and displays it as one. Our second example here, we have a structure that sits solely within the beam width and one that sits without. Because we're not catching any of that one that is without, the machine says, great, I think there's only one thing there, and displays it correctly. Again, our narrowest part is at that focal zone, and typically lateral resolution improves anywhere in the near zone, but it is best at the focal zone. And contrary to that then, it is worse in the far zone. Again, we have 2 structures that are sitting somewhere within the beam. Machine can't tell them apart, so it displays them as one. To correct it then, we're going to need to adjust our focus to the point of interest. So we're making the thinnest part of our beam at the focal point, or we're going to add focal zones to make the beam thinner in more spots. So the last resolution artifact is elevational resolution artifact, and we've touched on elevational resolution before in that there is actually a thickness to the ultrasound beam. It's not just this really, really thin slice. It actually has a little bit of width to it. It's still narrowest at the focal point and diverges in the far zone, so it's thicker in the far zone. But we do know that sound beams are 3D and they vary in thickness along the path. Again, thinnest at focal zone, and then it increases in that far zone. If an object is located within the beam in a plane perpendicular to the 2D image, then it may be displayed. So for example, we've got our beam coming out this way, and then we have that thickness to it. So if there's anything hanging out anywhere in this thickness part here, then it's going to be displayed in anything that intersects that front top, or the top part of our beam as well. So again, we have our beam coming out of the transducer face. We've talked about that there is a thickness to the beam. So if anything is showing up up on this main part of the axis, and then anything else hangs out somewhere else within the thickness of the beam, then it's kind of a conglomeration of the two are put together. You're going to get a little bit of that second reflector superimposed onto your main reflector. So up in the corner here we have a bladder, and we're getting that slice thickness artifact with just this little bit of kind of junky stuff down in the bottom here. It looks a lot like sludge in the gallbladder, or just some sort of low-level echoes within an area that should really be anechoic. Most likely in the bladder here, there is probably some bowel back behind into the beam, and it's just being displayed then into our main axis beam. So to correct it, we're going to use harmonics. That's going to reduce that extra noise, get rid of all these little echoes that are in there, or as you guys have already learned, you're going to use a 1.5 array transducer because they create thinner slices. So what assumptions then are in violation? The answer is that the sound beam is extremely thin. That was one of our 7 violations or 7 assumptions that the sound is violating, and we're getting those low-level echoes. So the last resolution artifact that we're going to see very commonly on our pictures are the speckle and noise. So speckle occurs right at the top of the near field, where there are small little wavelets that are going to interfere with one another. So we have our field, and it's all going to happen right in that first centimeter. We're going to get a lot of junk right up at the top here. It is not going to be displaying true anatomy, and it's going to actually degrade our image quite a bit right in those first few centimeters of the image. So that is why it's considered artifact, because it's not true anatomy. We're not truly seeing the skin layers like we would expect, because those are the first things that the sound is going through. We also can have noise artifact, and this is going to be seen as interference throughout the whole image. So again, this is no relation to true anatomy, and sometimes we'll see it as electronic interference. You'll find if you go up to the floors, like in the ICU or into surgery, there's just a lot of electronics that are going on that are going to interfere with how the picture looks on our machines. There's also biological interference. When people talk, it actually kind of jumbles everything, can cause interference with our pictures. Bowel rumbling around can cause some interference with our pictures. So there's actually biological reasons why interference would come in, noise interference would come in as well. You'll find with noise interference, especially if it's electrical noise interference, you're going to get these kind of lines that go all the way across your picture. Typically, this can be fixed then just by changing a probe to a different frequency, so they're just not sitting on that same frequency and interfering with one another. Harmonics is also another way to help speckle and noise. We know that harmonics gets rid of some of those little extra noises that come from the fundamental imaging. So switching over to harmonics is really going to help with our speckle. And then if we set the power of the machine appropriately, if you remember, power affects the noise or signal to noise ratio. If our power is set appropriately, then we can also get rid of some of that extra noise. So some machines now even have a speckle reduction knob or a capability that you can turn on and off. So this first picture here has the speckle reduction off. And if you look at the kind of echo texture of everything that's in that picture, we can really see how grainy it is. We're seeing little echoes within our carotid, and everything just looks really grainy. Once we turn the speckle reduction off, it really smooths everything out, and it makes our borders a little bit crisper, gets rid of those little yucky, junky little things that are all over our picture. So this would definitely be a more ideal picture, especially for vascular imaging. Bottom two pictures here are a couple of examples of electrical interference. So again, electrical interference usually is some sort of lines coming across your machine. I have seen ones where they kind of are like bows coming across, and you can see them kind of undulating through the whole image. It's not uncommon in heart surgery. If this is a picture of a TE on the heart, and we're actually getting a little cauterization interference from them using the electrocautery. So happens often in surgery, happens often up on the floors where there's lots of machines going on. Again, switching transducers to get rid of that electrical noise, or even just kind of dealing with it. You just have to probably deal with the heart one. You're not going to switch your probes on a TEE. All right, so that was it for resolution artifacts. So again, axial, lateral, slice thickness, and then speckle and noise all affect the resolution on our machine and the artifacts that arise from them. So let's go ahead and test ourselves. So number 1, which resolution has changed between I and II, or 2? What did the sonographer most likely change between these two pictures? Number 2, which resolution artifact is often seen in structures that should be anechoic because the machine is picking up echo information from the entire thickness of the beam? Number 3, this phantom is testing lateral resolution where all of the circles are. There should be 5 dots at each level. Explain why each level looks different and why some do not have 5 dots. And number 4, again, think of a question that you have about this lecture. What didn't make sense to you? If you are comfortable with everything that we just talked about, then go ahead and write a test question, something that you know that you understand, maybe could even explain to another student.